In the silence between starlight and shadow, where the universe keeps its oldest secrets, a machine of human ingenuity has looked backward through time itself. The James Webb Space Telescope, floating 1 million miles from Earth in the cosmic deep, has turned its golden eyes toward the very edge of existence. And what it found there, in the darkness of the cosmic dawn, is not merely surprising, it is terrifying. 13 billion years ago, in the first moments after the universe emerged from its primordial fire, something happened that should not have been possible. Galaxies formed too quickly, stars burned too brightly, black holes grew to impossible sizes in what should have been an infant cosmos. The laws we thought governed creation, the gentle progression from simple to complex, from darkness to light, appear to have been violated on a scale we're only beginning to comprehend. The universe's birth was not the quiet, orderly emergence we imagined. It was violent, chaotic, and profoundly unsettling. Tonight, we will journey backward through time itself, following the light that has travelled across billions of years to reach us. We will drift beyond the familiar stars, beyond the galaxies visible to older telescopes, into a realm where the universe was barely a fraction of its current age. Here, in this ancient darkness, James Webb has discovered things that challenge the very foundations of cosmology. Galaxies that should not exist. Black holes impossibly massive for their age. Elements forged in stellar furnaces that somehow appeared too soon. These are not minor anomalies. They are cracks in the story we have told ourselves about where we come from and how everything began. The cosmic dawn. Scientists call it the epoch of first light, the moment when the universe's darkness finally surrendered to illumination. For hundreds of millions of years after the Big Bang, the cosmos existed in what astronomers call the Dark Ages. No stars, no galaxies, only hydrogen, helium, and the faint echo of creation's first light slowly cooling into invisibility. Then gradually gravity began its patient work, pulling atoms together, forming the first clouds, and within those clouds the first stars ignited. These were not stars like our sun. They were monsters, hundreds of times more massive, burning with such ferocious intensity that they lived fast and died young, exploding across the infant universe and seeding it with heavier elements. Or at least, that is what we believed. James Webb has shown us a different story, one where the timeline compresses impossibly, where galaxies appear fully formed in cosmic infancy, where the universe seems to have evolved far faster than our models predicted. It is as if we've opened a history book expecting to read about simple villages, and instead found sprawling civilizations, complete with architecture, culture, and technology that should have taken millennia to develop. The universe, it seems, was in a hurry, and we do not yet understand why. This is not merely an academic curiosity. These discoveries strike at the heart of our understanding of physics, time, and existence itself. If the early universe behaved differently than we thought, if the rules were different then, what does that mean for everything we think we know? What does it mean for the future? The terrifying beauty of Webb's discoveries is that they remind us how little we truly comprehend about the cosmos we inhabit. Tonight, we invite you to drift with us into this unsettling realm, to witness through Webb's unprecedented vision what lies at the very edge of time, to confront the monsters lurking in the universe's cradle, and to ask the questions that emerge when our certainties dissolve into wonder and unease. This journey will take us across billions of years, through epochs of cosmic transformation, to the very boundary where observation meets the unknown. Before we begin this voyage into deep time, we would love to know where you are in your own moment. Please take a moment to comment below and tell us where you are watching from and what time it is in your corner of Earth. Are you drifting towards sleep as night settles around you? Or perhaps you are greeting the dawn, watching this as a new day begins. Wherever you are, whatever hour marks your present, know that we are all sharing this moment together, looking backward through time from our tiny island in the cosmos. Now, settle in. Let the weight of the day release its hold. Allow your mind to expand beyond the familiar boundaries of human time. Let us begin our descent into the cosmic dawn, where James Webb has illuminated terrors written in the language of ancient light. In the darkness of space, 1.5 million kilometers from Earth, a machine floats in perfect silence. It is not a probe designed to touch distant worlds. It is not a lander built to walk upon alien soil. It is something far more profound. A telescope so powerful, so exquisitely engineered, that it can pierce through the fabric of time itself and show us the universe as it was when creation was still young. This is the James Webb Space Telescope, and its journey to the edge of time is not measured in distance alone, but in the depths of cosmic history it has unveiled. To understand what Webb sees, we must first understand what it is. This is no ordinary telescope. Its primary mirror spans 21 feet across, composed of 18 hexagonal segments made of gold-plated beryllium. Each segment is polished to nanometer precision, working together as a single reflective surface larger than any mirror ever sent into space. Yet despite its size, Webb is impossibly light. Designed to fold like origami during launch, then unfurl in the vacuum of space like a mechanical flower blooming in darkness. The engineering required to achieve this borders on the impossible. Every component must withstand the violence of launch, the cold of space, and the precision demands of optics so fine they could detect the heat signature of a bumblebee on the moon. But it is not the mirror alone that makes Webb extraordinary. It is what the mirror sees. Unlike the Hubble Space Telescope, which observes primarily invisible light, Webb peers into the infrared spectrum, a range of light invisible to human eyes but essential for observing the ancient universe. Infrared light pierces through cosmic dust and gas that would otherwise obscure our view. More importantly, it allows Webb to see light that has been stretched across billions of years of cosmic expansion, light that left distant galaxies when the universe was still in its infancy. This is the science of redshift, and it is the key to measuring time itself across the cosmos. As the universe expands, the space between galaxies stretches, and the light travelling through that space stretches with it. Light that was once blue or ultraviolet shifts toward red and infrared, its wavelength elongated by the expansion of space. The farther away a galaxy is, the longer its light has travelled and the more it has been redshifted. By measuring this shift, astronomers can calculate not just distance but time. They can determine when that light was emitted, how long ago the universe existed in that state, and what the cosmos looked like in its earliest epochs. Webb's infrared vision is so sensitive it can detect light that has been travelling for more than 13 billion years, light emitted when the universe was only a few 100 million years old. This is light from the cosmic dawn, the era when the first stars ignited, the first galaxies formed, and darkness gave way to illumination for the first time in cosmic history. To see this light is to look backward through time, to witness creation unfolding frame by frame in reverse. But to achieve this vision, Webb had to journey far from Earth. Unlike Hubble, which orbits our planet at an altitude of just 340 miles, Webb resides at a location known as the second Lagrange point, or L2. This is a gravitationally balanced point in space where the pull of Earth and the Sun combine in such a way that a spacecraft can remain in a stable position relative to both bodies without expending significant fuel. L2 lies approximately 1.5 million kilometers from Earth, 4 times farther than the Moon, on the side opposite the Sun. This location is ideal for deep space observation. At L2, Webb is shielded from the heat and light of the Sun, Earth, and Moon by a massive 5-layer sunshield the size of a tennis court. This sunshield keeps the telescope's instruments at temperatures near absolute zero, cold enough to detect the faint infrared glow of distant galaxies without interference from ambient heat. In this frozen silence suspended between worlds, Webb operates with a clarity that would be impossible anywhere else. The journey to L2 was itself a marvel of precision, unlike missions to planets or moons. There was no dramatic landing, no fiery descent through an atmosphere. Webb simply coasted through space, nudged gently by small thruster burns, unfolding its sunshield and mirror segments with painstaking care. Each deployment was a moment of tension. A single stuck hinge, a single failed motor could have rendered the entire mission useless. But one by one, the segments locked into place. The sunshield unfurled without error, and the telescope, after decades of planning and engineering, opened its eye to the cosmos. The difference between Webb and Hubble is not just technical, it is philosophical. Hubble showed us the universe in the light we know, the light our eyes evolved to see. It revealed galaxies swirling in majestic spirals, nebulae glowing with ionized gas, and planets orbiting distant stars. Hubble gave us beauty, clarity, and wonder. But there were limits to what it could see. Beyond a certain distance, beyond a certain point in time, the universe becomes shrouded in darkness and dust. The light from the earliest galaxies, red-shifted into the infrared, remained invisible to Hubble's instruments. Webb sees what Hubble could not. It peers through the dust of star-forming regions, revealing protostars hidden within collapsing clouds of gas. It examines the atmospheres of exoplanets, detecting molecules that could hint at habitability or even life. But most profoundly, it looks farther back in time than any telescope before it, into the epoch known as the Cosmic Dawn, when the first light in the universe pierced the primordial darkness. When Webb's first deep field image was released, the world held its breath. The image covered a patch of sky no larger than a grain of sand held at arm's length. Yet within that tiny sliver of space, Webb revealed thousands of galaxies, each one a swirling mass of billions of stars, stretching across billions of light years. Some of these galaxies appeared as they were only a few 100 million years after the Big Bang. They were not the large, mature spirals we see in the nearby universe. They were small, irregular, chaotic, still forming, still gathering mass from the cosmic web of dark matter and hydrogen gas that filled the early universe. But what stunned astronomers was not just the number of galaxies, it was their nature. Some of these early galaxies were brighter, more massive, and more structured than anyone had predicted. According to prevailing models, galaxies should have grown slowly over billions of years, accumulating mass gradually through mergers and star formation. Yet here were galaxies, formed in the cosmic dawn, that appeared surprisingly mature, surprisingly organized, as if they had aged faster than the universe should have allowed. This was not just a surprise, it was a challenge to our understanding of cosmic evolution. How could galaxies form so quickly? How could they become so massive in such a short time? The answer lies hidden in the data, in the redshift, measurements in the spectra of light Webb continues to collect. But it is an answer that may force us to rewrite the story of creation itself. The technical challenges Webb overcame to make these observations are staggering. To detect light from galaxies 13 billion light-years away requires not just a large mirror, but instruments capable of isolating individual photons that have travelled across the entire observable universe. Webb's instruments include near-infrared cameras, spectrographs that split light into its component wavelengths, and coronagraphs that block the light of stars to reveal faint objects nearby. Each instrument operates at temperatures near -230 degrees Celsius, cold enough that any stray heat would drown out the faint signals from distant galaxies. The telescope's optics are aligned with such precision that any deviation, even by nanometers, would blur its vision. To achieve this, engineers developed a system of actuators behind each mirror segment, tiny motors that adjust the position of each hexagon with micrometer accuracy. These adjustments are made continuously, compensating for thermal expansion, micrometeoroids, and the subtle gravitational influences of the Sun and Earth. In this way, Webb's mirror remains perfect, a flawless lens through which the ancient universe reveals itself. Every image Webb captures is not just a photograph, it is a time capsule. The light in these images is older than the pyramids, older than dinosaurs, older than Earth itself. It is light that has travelled through expanding space for billions of years, carrying with it the story of galaxies that may no longer exist, stars that have long since died, and structures that have evolved into forms unrecognizable from their origins. To look at a Webb image is to see not just space, but time itself laid bare. As Webb continues its mission, it will observe not just galaxies, but the chemistry of the early universe. It will detect the signatures of elements forged in the first stars, trace the formation of black holes in the hearts of infant galaxies, and search for the molecules that could indicate life on distant worlds. Each observation adds a piece to the puzzle, a fragment of understanding in our quest to comprehend how the universe began, how it evolved, and what it will become. Yet there is something unsettling in what Webb reveals. The universe it shows us is not the universe we expected. The galaxies are too bright, too massive, too organized. They challenge our models, defy our predictions, and force us to ask uncomfortable questions. Are our theories of cosmic evolution incomplete? Is there something fundamental about the early universe we do not yet understand? Or is the universe itself stranger, more complex and more terrifying than we ever imagined? Webb does not answer these questions with certainty. It offers only observations, data points scattered across the canvas of time. But in those observations lies a truth we cannot ignore. The universe is not static. It is not simple. It is a living tapestry woven from forces and processes we are only beginning to comprehend. And in the cold silence of space, suspended at the Lagrange point between worlds, a machine built by human hands continues to watch, to measure, to reveal. The James Webb Space Telescope is not just a tool. It is a bridge between the present and the past, between knowledge and mystery. It carries with it the hopes of a species that looks up at the stars and asks the oldest question of all: where did we come from? And in the faint glow of galaxies born at the edge of time, Webb whispers back an answer, not in words but in light. Light that has travelled farther and longer than anything in human experience. Light that shows us not just what the universe was, but what it is becoming. As we prepare to follow Webb's gaze deeper into the cosmic dawn, we must brace ourselves for what lies ahead. For in looking backward through time, we're not just discovering history, we're confronting the origins of existence itself, and what we find there may be more terrifying than we ever imagined. For nearly 380,000 years after the Big Bang, the universe was invisible. Not dark in the way we understand darkness, but opaque, a churning fog of plasma so dense that light itself could not travel. Photons scattered endlessly, trapped in a cosmic haze where nothing could be seen, nothing could form, and nothing could exist as we know it today. Then, suddenly the universe cooled. Electrons and protons combined to form the first hydrogen atoms, and light was set free. This moment, known as recombination, marked the birth of transparency. The universe became clear, but it was not yet illuminated. What followed is called the Dark Ages, and the name is profoundly literal. For hundreds of millions of years, the cosmos existed in absolute blackness. There were no stars, no galaxies, no light sources of any kind. Only vast clouds of neutral hydrogen drifting through the void, cooling slowly, waiting. Space was not merely empty, it was dormant, a sleeping giant in the moments before its awakening. The universe had expanded, cooled, and settled into an eerie stillness. Yet within that darkness, gravity was working, silently, invisibly, pulling matter together in ways we're only beginning to understand. This period stretched from roughly 380,000 years after the Big Bang to somewhere around 100 million years, though the exact timeline has always been uncertain. No telescope could ever see this era directly, because there was nothing to see. No light existed. No stars had ignited. The universe was a blank canvas, waiting for the first brushstroke of illumination. Scientists could only theorize what happened during this time, constructing models based on mathematics and the faint echoes of radiation left over from the Big Bang itself. Then came the cosmic dawn, the moment when darkness ended, not gradually but suddenly, violently, as the first stars ignited across the universe. These were not stars like our sun, gentle and stable. They were monsters, hundreds of times more massive, burning with unimaginable ferocity. Their light tore through the surrounding hydrogen, ionizing it, carving bubbles of transparency into the fog. This process, called reionization, transformed the universe from a dark, neutral sea into a brilliant, ionized expanse. The cosmic dawn was not a sunrise. It was an explosion of light that changed the very structure of reality. For decades, cosmologists believed they understood this process. The first stars were expected to form around 100 to 200 million years after the Big Bang. They would be massive but short-lived, burning out quickly and seeding the universe with heavier elements. From their ashes, the first galaxies would slowly assemble, small and primitive, gradually growing over billions of years into the grand spiral and elliptical galaxies we see today. This was the timeline. This was the story written in textbooks, carved into models, and accepted as truth. Then the James Webb Space Telescope looked into the cosmic dawn, and what it found shattered everything. Webb's infrared eyes pierced through billions of years of expanding space, capturing light that had been travelling since the universe was only a few 100 million years old. What astronomers expected to see were faint, small, irregular clumps of stars, the infant galaxies of a young cosmos. What they saw instead were fully formed galaxies, massive, structured and mature, existing at times when they simply should not exist. Galaxies with billions of stars, galaxies with organized spiral arms, galaxies so bright and so large that their presence defied every model of cosmic evolution. One galaxy, catalogued as Glass Z13, appeared to exist just 300 million years after the Big Bang. Another, Sears, 93,316, seemed to push even further back, to 235 million years. These were not primitive stellar nurseries. They had developed systems glowing with the light of countless stars, structured and stable as if they had been forming for billions of years, not mere hundreds of millions. The timeline had collapsed. The universe, it seemed, had grown up far too quickly. The problem is not just that these galaxies exist early, it is that they are impossibly massive. According to our understanding of physics, matter cannot accumulate fast enough to build such large galaxies in such short time spans. After the Big Bang, the universe was nearly uniform, with only tiny fluctuations in density. Gravity would pull matter together slowly, forming the first stars, then small clusters, then larger structures over time. This process is gradual, constrained by the speed of gravitational collapse and the rate at which gas can cool and condense. Yet, Webb observed galaxies with masses equivalent to billions of suns, fully assembled when the universe was barely out of infancy. To form these structures so quickly would require gravity to work faster, matter to collapse more efficiently, and star formation to occur at rates far beyond what our models predict. It is as if the universe skipped several chapters of its own story, leaping from birth to adulthood in a fraction of the expected time. Some of these early galaxies are not just massive, they are mature. They possess features that suggest long evolutionary histories, distinct stellar populations, heavy element enrichment, organized structures. On Earth, it takes billions of years for complex ecosystems to evolve. In the early universe, galaxies appear to have evolved in hundreds of millions, a timescale so compressed it challenges the very laws we thought governed cosmic development. The implications reach beyond galaxy formation. They touch the foundations of cosmology itself. Our models of the universe depend on dark matter, an invisible substance that makes up most of the mass in the cosmos. Dark matter's gravity is what pulls ordinary matter together, forming the scaffolding upon which galaxies are built. If galaxies form too quickly, it suggests that either dark matter behaves differently than we thought, or that some other force, some unknown mechanism, accelerated the process in ways we do not understand. Perhaps dark matter was denser in certain regions than our models predict. Perhaps the first stars were far more efficient at triggering subsequent generations of star formation. Or perhaps there is something fundamentally wrong with our understanding of how gravity operates on cosmic scales in the earliest epochs of time. Each possibility is unsettling. Each one requires rewriting portions of the cosmic narrative we've spent decades constructing. But the terror does not end with galaxies. Embedded within some of these impossibly early structures, Webb detected signatures of supermassive black holes. Not the remnants of dead stars, but black holes millions of times the mass of the Sun, already feeding, already growing, already dominating the centers of their galaxies. These objects present an even deeper mystery. Supermassive black holes are supposed to take time to form. A star collapses into a small black hole, which then feeds on surrounding gas and merges with other black holes over billions of years, slowly accumulating mass. Yet Webb found supermassive black holes existing when the universe was less than 1 billion years old, far too early for the slow accumulation process to account for their size. Some of these black holes are so massive that they should not exist at all. Not yet, not in a universe so young. One theory suggests that these black holes formed directly from the collapse of massive gas clouds in the early universe, bypassing the stellar stage entirely. Another proposes that the first black holes grew at rates far exceeding current theoretical limits, gorging themselves on matter in a cosmic feeding frenzy. Both ideas push the boundaries of known physics. Both suggest that the early universe was far more chaotic, far more extreme than we ever imagined. The discovery of these ancient supermassive black holes also forces us to reconsider the relationship between black holes and galaxies. Modern galaxies and their central black holes appear to evolve together, each influencing the other's growth. But if black holes existed before their galaxies were fully formed, it suggests that black holes may have played a role in galaxy formation itself, shaping the cosmos from the very beginning, acting as seeds around which entire systems of stars and gas condensed. This is where the word terrifying begins to take on its full meaning. Not terrifying in the sense of fear, but in the sense of confronting the unknown, of realizing that the universe does not follow the rules we thought we had written. For cosmologists and physicists, these discoveries are profoundly unsettling because they reveal how little we truly understand about the earliest moments of cosmic history. Every model, every simulation, every prediction about the cosmic dawn was based on assumptions about how matter behaves, how gravity works, and how structures form over time. Webb's observations suggest that those assumptions may be incomplete, or worse, fundamentally flawed. It is as if we have been reading a book in a language we thought we understood, only to discover that entire chapters are written in symbols we cannot decipher. The universe was supposed to evolve slowly, methodically, building complexity over eons. Instead, it erupted into form with shocking speed, assembling galaxies and black holes in timeframes that defy explanation. This acceleration, this cosmic precocity, hints at forces or processes we have not yet identified. Perhaps the physics of the early universe operated under different conditions, with different constants, different rules. Perhaps the interplay between dark matter, dark energy, and ordinary matter was far more dynamic than our models suggest. What Webb has shown us is not just a collection of distant galaxies. It is a mirror held up to our understanding of existence itself. These ancient structures, impossibly large and impossibly early, are evidence that the story of the universe is not the story we've been telling. The cosmic dawn did not unfold as predicted. Darkness did not give way to light gradually. It exploded into brilliance, and with that explosion came structures so advanced, so developed, that they challenge the very timeline of creation. As we stare into these images, at galaxies glowing in the deep infrared, we're not simply looking back in time. We're witnessing the birth of cosmic horror, not the horror of monsters or malevolent forces, but the horror of realizing that the universe is stranger, faster, and more mysterious than we ever dared imagine. The cosmic dawn has ended, but the questions it raises have only just begun, and in the silence of space among the light of ancient stars, the universe whispers a truth we are only beginning to hear. We do not yet understand how we came to be. In the darkness before memory, before stars had names and galaxies had shapes, something impossible was unfolding. James Webb looked into that ancient abyss and found structures that should not exist, galaxies so massive, so organized, so impossibly mature that they force us to question everything we believed about the birth of the cosmos. These are not merely distant objects. They are violations of cosmic law, monuments to mysteries we have yet to comprehend. The first shock came from a galaxy designated JD's GS Z13-0, a cryptic string of letters and numbers that masks the profound terror of its discovery. This galaxy exists so far back in time that its light has travelled for over 13.4 billion years to reach us. We are seeing it as it was just 320 million years after the Big Bang, a mere cosmic heartbeat after creation itself. At that moment in history, the universe was supposed to be primitive, chaotic, and dark, still assembling its first fragile structures from clouds of hydrogen and helium. Instead, Webb revealed a galaxy already blazing with the light of countless stars, a fully formed island of matter suspended in an ocean of primordial night. But JD's GS Z13-0 was only the beginning. As Webb's instruments continued their patient vigil, more ultra-distant galaxy candidates emerged from the data. Each one pushed the boundaries of cosmic time further backward. Each one appeared larger and brighter than cosmological models predicted. These galaxies should have been faint, struggling embers barely visible against the cosmic microwave background. Instead, they shine with an intensity that defies explanation, as if someone had lit 1,000 suns in an era when even a single star was considered extraordinary. What makes these discoveries truly unsettling is not just their distance, but their mass. Several of these ancient galaxies contain stellar masses equivalent to billions of suns, perhaps even tens of billions. This presents a fundamental paradox. Building such massive structures requires time, immense spans of time for gas to collapse, for stars to form, for generations of stellar death and rebirth to forge new elements. Yet here they are, fully formed, impossibly heavy, existing in an epoch when the universe was supposedly too young to have assembled anything so grand. The numbers refuse to reconcile. Current models suggest that the first galaxies should have taken hundreds of millions of years to accumulate significant mass. But these cosmic monsters appear to have bypassed that gradual process entirely, assembling themselves with impossible speed. It is as if we discovered a skyscraper standing complete on the day the foundation was poured, or found a forest of ancient oaks growing from seeds planted only yesterday. Time itself seems broken in these observations. Among the most perplexing discoveries are what astronomers have begun calling the little red dots. These are compact, extraordinarily bright objects that appear scattered throughout Webb's deep field images of the early universe. They glow with a crimson hue, their light stretched into the red end of the spectrum by the expansion of space itself. But their nature remains deeply ambiguous. Are they galaxies? Are they something else entirely? Their brightness suggests enormous energy output, yet their compactness defies easy classification. Some of these little red dots shine with the luminosity of entire galaxies, yet occupy a space no larger than our solar system. This combination of extreme brightness and tiny size has led to fierce debate among cosmologists. Some believe they could be supermassive black holes, their accretion disks blazing as matter spirals inward. Others suggest they might be dense clusters of massive stars, packed so tightly together that they create a unified blaze of light. Still others propose more exotic explanations: primordial quasars, dark matter interactions, or phenomena we've not yet named because we lack the framework to understand them. What makes the little red dots particularly unsettling is their abundance. They are not rare anomalies. They appear throughout the ancient universe in numbers that exceed predictions by orders of magnitude. If each one represents a massive structure, then the early universe was far more crowded, far more active, and far more organized than we ever imagined. The cosmic dawn, it seems, was not a gradual awakening but an explosive eruption of complexity. Webb's observations have also revealed tantalizing evidence of population Theta stars, the theoretical first generation of stars that formed from the pristine hydrogen and helium created in the Big Bang. These stars have never been directly observed before because they should have died billions of years ago, collapsing into black holes or exploding as supernovae. Yet buried within the spectral data from some of these ancient galaxies are chemical signatures that match theoretical predictions for population 3 stellar atmospheres. The primordial giants would have been unlike any stars visible in the modern universe. With no heavy elements to regulate their internal fusion, they would have burned impossibly hot and bright, perhaps reaching masses hundreds of times greater than our Sun. They would have lived fast and died young, seeding the cosmos with the first carbon, oxygen, and iron. Finding evidence of their existence is like discovering a fossil of the universe's first breath. But their presence in such organized galactic structures raises more questions than it answers. How did these first stars form so quickly? How did they assemble into coherent galaxies almost immediately after, igniting? Perhaps most troubling is the apparent maturity of these ancient galaxies. When we examine their light in detail, many show signs of sophisticated structure. Spiral arms, central bulges, organized rotation patterns. These are features we associate with galaxies that have evolved over billions of years, shaped by countless gravitational interactions and stellar generations. Finding them in galaxies less than 500 million years old is like discovering a butterfly emerging from a cocoon that was formed only moments before. The universe, it seems, knew how to build galaxies long before we thought it learned the skill. These ancient structures appear too ordered, too stable, too familiar. They possess a symmetry and architecture that should have required eons to develop, yet they materialized almost instantly on cosmic timescales. It is as if the universe had a blueprint from the very beginning, a set of instructions that allowed complexity to emerge far faster than physics should permit. This accumulation of impossible observations has created what many scientists now call a crisis in cosmology. The lambda CDM model, our standard cosmological framework, has successfully explained countless observations for decades. It describes a universe composed of dark matter, dark energy, and ordinary matter, evolving according to well-understood gravitational and quantum mechanical principles. According to this model, structure formation should proceed hierarchically, with small objects forming first and gradually merging into larger ones over billions of years. But Webb's discoveries challenge this careful framework. The galaxies we observe in the cosmic dawn are too massive, too mature, and too numerous to fit comfortably within lambda CDM predictions. Either our observations are somehow systematically flawed, which seems increasingly unlikely given the telescope's precision, or something fundamental about our cosmological model requires revision. The ground beneath our theoretical feet has begun to shift. Some physicists have begun proposing modifications to the standard model. Perhaps dark matter behaves differently than we assumed, clumping together more efficiently in the early universe. Perhaps the initial conditions following the Big Bang were not as uniform as we believed, allowing pockets of enhanced density to form massive structures rapidly. Perhaps there are exotic processes, quantum effects operating on galactic scales, or interactions between dark energy and matter that we have not yet incorporated into our equations. Other researchers suggest more radical alternatives. Some propose that the speed of light might have been different in the very early universe, allowing information and matter to travel faster and enabling rapid structure formation. Others revive older theories of modified gravity, suggesting that Einstein's general relativity itself might need adjustment when applied to the extreme conditions of the cosmic dawn. These ideas remain speculative and controversial, but the weight of Webb's observations grows heavier with each new data release. There is also the uncomfortable possibility that we have fundamentally misunderstood cosmic time itself. Our measurements of distances and ages in the universe rely on chains of assumptions, the constancy of physical laws, the interpretation of redshift as cosmic expansion, the calibration of standard candles used to measure distance. If any link in this chain contains an error, our entire timeline could be wrong. Perhaps these galaxies are not as distant or ancient as we calculate. Perhaps the universe is older than we think. Perhaps time, in the extreme environment following the Big Bang, flowed differently than it does in the modern cosmos. Yet even if such radical revisions prove necessary, the core mystery remains. These galaxies exist. Their light has reached us. Their structures are real. Whether they are 300 million years old or 500 million or some other age entirely, they are too massive and too organized for comfort. They represent a cosmic reality that resists our attempts at explanation. As we stare at these images, these little red dots scattered across Webb's field of view like drops of blood on ancient parchment, we confront something more profound than a scientific puzzle. We face the realization that the universe, in its infancy, was capable of feats we cannot yet comprehend. It assembled complexity from chaos far faster than our best theories allow. It created order from darkness with terrifying efficiency. The monsters in the infant universe are not dragons or demons. They are galaxies, structures made of ordinary matter obeying physical laws, yet their very existence challenges everything we thought we knew about cosmic evolution. They force us to acknowledge that nature, even when bound by mathematics and physics, remains capable of surprise. The early universe was not a simple place gradually becoming complex. It was, from nearly the first instant, a realm of staggering intricacy and power. In the silence of deep space, across billions of years, these ancient galaxies shine with light that began its journey when the cosmos was young. That light carries a message, though we struggle to read it. It tells us that reality is stranger than our theories, that the universe has secrets embedded in its oldest structures, and that the cosmic dawn was not a gentle sunrise, but a violent, inexplicable eruption of creation. As Webb continues its observations, penetrating deeper into cosmic time with each passing month, we brace ourselves for more revelations, more impossible galaxies, more structures that defy explanation, more evidence that the universe, in its earliest moments, played by rules we have yet to discover. The monsters are real, and they are rewriting the story of existence one impossible galaxy at a time. In the silence of deep space, James Webb has found something that defies comprehension, something that should not exist. Not yet. Not so soon after the universe began. At the edge of time itself, in galaxies barely 500 million years old, there are monsters. Black holes so massive, so impossibly ancient, that their very existence threatens to unravel everything we thought we understood about cosmic evolution. These are not the black holes of stellar death, formed from collapsed stars. These are supermassive titans weighing millions, even billions of times the mass of our sun. And they are everywhere in the cosmic dawn, glowing like demonic eyes in the infant universe. The discovery is not just surprising, it is terrifying. because according to every model, every theory, every simulation we've constructed, these black holes should not have had time to grow. The universe was too young, the timeline too compressed, and yet there they are, waiting in the darkness, challenging us to explain how the cosmos could birth such colossal predators in what amounts to its first breath. James Webb has peered into galaxies less than 500 million years after the Big Bang and found supermassive black holes at their centers. To understand how unsettling this is, we must grasp the scale of time involved. 500 million years sounds like an eternity to human minds, but in cosmic terms, it is barely a moment. It is the universe's infancy. The first stars had only just begun to ignite. Galaxies were still assembling from clouds of hydrogen and helium. The cosmic web, that vast structure of filaments and voids, was only beginning to take shape, and yet already black holes weighing billions of solar masses were lurking at the hearts of these newborn galaxies, feeding voraciously, growing impossibly fast. This is the black hole seed problem, one of the most profound mysteries uncovered by James Webb's observations. Black holes grow by consuming matter. Stars, gas, dust, anything that ventures too close to the event horizon is devoured, adding to the black hole's mass. But this process takes time. A stellar mass black hole, born from the death of a massive star, might weigh 10 or 20 times the mass of the Sun. To grow from that into a supermassive black hole weighing 1 billion solar masses requires feeding continuously for millions, even hundreds of millions of years. But the universe at 500 million years old had not existed long enough for this gradual accumulation to occur. The math simply does not work. The timeline is too short. The black holes are too large. Something else must have happened. Something rapid. Something violent. Something we do not yet understand. Scientists have proposed several theories to explain these cosmic anomalies. One of the most compelling is the concept of direct collapse black holes. In this scenario, under very specific conditions in the early universe, vast clouds of primordial hydrogen gas could collapse directly into black holes without forming stars first. These would not be small black holes. They would be born massive, weighing tens of thousands, perhaps even hundreds of thousands of solar masses from the very beginning. This head start would give them time to grow into the supermassive titans we observe today. But direct collapse requires extraordinary circumstances. The gas must be kept pristine, free from heavier elements that would cool it and allow star formation. It must collapse rapidly, under the influence of intense ultraviolet radiation from nearby sources. The conditions must be perfect, and the window of opportunity brief. Another theory reaches even further back into the mists of creation. Primordial black holes. These hypothetical objects would have formed not from stars or collapsing gas, but from density fluctuations in the first moments after the Big Bang itself, before the first stars, before the first galaxies, perhaps even before the first atoms. If such black holes existed, they would have been scattered throughout the early universe, waiting silently in the darkness, ready to serve as the seeds from which supermassive black holes eventually grew. But detecting or proving the existence of primordial black holes remains one of the great challenges of modern astrophysics. They are ghosts in the cosmic machine, theoretical entities that could solve our problems if only we could confirm they exist. James Webb's observations force us to confront what cosmologists call the chicken and egg problem. Did galaxies form first and then create black holes at their centers? Or did black holes form first and their immense gravity pull surrounding gas and stars together to form galaxies? For decades, the conventional wisdom held that galaxies came first, slowly assembling through gravity until dense regions at their cores collapsed into black holes. But the supermassive black holes in the cosmic dawn challenge this narrative. Some of these black holes appear to have formed too quickly, too early, suggesting that they may have preceded their host galaxies. Perhaps black holes were the seeds around which galaxies coalesced. Perhaps these monsters shaped the very structure of the universe. The evidence is mounting. James Webb has detected active galactic nuclei in some of the earliest galaxies ever observed. These are not quiet, dormant black holes. They are feeding frenzies. Matter spirals inward toward the event horizon, forming accretion disks that heat to millions of degrees, emitting torrents of radiation across the electromagnetic spectrum. These active galactic nuclei shine with the light of trillions of suns, outshining entire galaxies. They are quasars, blazers, cosmic beacons powered by black holes consuming mass at an almost unimaginable rate. And they existed when the universe was still in its infancy. What makes this discovery even more unsettling is the proportion. In some early galaxies observed by James Webb, the central black hole appears to weigh as much as, or even more than, the entire visible mass of stars in the galaxy itself. This is unprecedented. In the modern universe, supermassive black holes typically account for less than 1% of their galaxy's total mass. But in the cosmic dawn, some black holes seem to dominate their galaxies, outweighing their stellar populations. It is as if the galaxy exists to feed the black hole, rather than the black hole being a byproduct of the galaxy's evolution. The cosmic hierarchy we thought we understood has been inverted. These ancient monsters tell us something profound about the fundamental nature of space-time. Black holes are not just massive objects. They are regions where the fabric of reality itself breaks down, where gravity becomes so strong that space curves infinitely inward, where time slows to a stop at the event horizon, where the laws of physics as we understand them cease to apply. To find such objects so early in the universe's history suggests that the conditions for extreme space-time distortion existed almost from the beginning. The universe did not slowly evolve toward complexity. It was born violent, chaotic, and filled with forces capable of tearing reality apart. Perhaps most haunting is the possibility that primordial black holes, if they exist, could still be scattered throughout the universe today, invisible, undetectable except through their gravitational influence. Some theories suggest that primordial black holes could even account for some or all of the mysterious dark matter that holds galaxies together. These ancient relics from the first fraction of a second after the Big Bang could be drifting through space, through galaxies, perhaps even through our own solar system, silent witnesses to the birth of everything. James Webb has opened a window into the cosmic dawn, and what it has revealed is not a gentle unfolding of order from chaos. It is a universe born in terror, a universe where black holes, the most destructive forces we know, were among the first structures to emerge. They did not wait for stars to die. They did not wait for galaxies to form. They appeared almost immediately, ravenous and unstoppable, shaping the universe around them through the sheer force of their gravity. To comprehend these black holes is to confront the limits of human understanding. We build our theories on observations of the present. We extrapolate backward, assuming that the past resembled the present, only younger. But James Webb shows us a past that is alien, a universe so different from our own that the rules we thought were universal may not have applied. Time moved differently. Gravity behaved differently. Black holes grew faster than should have been possible, and we're left with questions that have no easy answers. How did these monsters form so quickly? Did they emerge from direct collapse, from primordial seeds scattered by the Big Bang? Or is there another mechanism entirely, something we have not yet imagined? Did galaxies form around black holes, or did black holes form within galaxies? And if black holes came first, what does that mean for the very concept of cosmic structure? Are galaxies merely the visible remnants of an invisible architecture built from gravity and darkness? The discovery of supermassive black holes at the edge of time is not just a scientific puzzle. It is a confrontation with the unknown. It is a reminder that the universe is older, stranger, and more violent than we ever imagined. These black holes are not anomalies. They are evidence that the cosmic dawn was not a peaceful awakening, but a birth marked by forces so powerful they could bend space-time itself. They are the ultimate cosmic horror. Not because they destroy, but because they existed before they should have. Before stars, before galaxies, before light. As we stare into the data transmitted by James Webb, we are not just looking at distant objects. We are looking into the abyss of time itself. And in that abyss, black holes stare back, ancient and incomprehensible, challenging everything we thought we knew about the beginning of existence. They are not relics of a dead past. They are architects of reality, present from the very start, shaping the universe in ways we are only beginning to understand. The black holes at the beginning of time are not just monsters, they are messengers. They tell us that the universe was never meant to be understood easily, that the cosmos does not conform to our expectations, that even at the edge of time, in the first flickering moments of creation, there were forces at work beyond our comprehension, forces that built the universe we inhabit today, forces that may still be shaping our destiny in ways we cannot yet perceive. In the silence of the cosmic dawn, James Webb has found the ultimate cosmic horror, not in the destruction black holes bring, but in their impossible existence. They should not be there, and yet they are, waiting in the darkness, challenging us to explain them, reminding us that the universe is vast, ancient, and filled with mysteries that may never be fully solved. The universe has rules. Elements are forged in the hearts of stars. Stars must live, burn, and die before heavier elements can exist. This process takes time, measured not in years, but in billions of years. Yet when James Webb turned its gaze toward the cosmic dawn, it found something that should not be there. Heavy elements, metals, oxygen, carbon, silicon, all present in galaxies so young they should contain nothing but hydrogen and helium, the primordial elements born in the Big Bang. What Webb discovered was not just unexpected, it was impossible according to everything we thought we knew about stellar evolution and the periodic table itself. This is the chemistry of terror, the revelation that the building blocks of reality appeared far too early, in concentrations far too high, defying the cosmic clock that should have governed their creation. To understand the horror of this discovery, we must first understand how elements are supposed to form, and then confront what it means when the universe breaks its own fundamental rules. In the beginning, there were only 3 elements: hydrogen, helium, and trace amounts of lithium. These were the children of the Big Bang, forged in the first minutes of existence when the universe was a seething cauldron of energy and matter. Everything else, every atom of carbon in our bodies, every molecule of oxygen we breathe, every grain of iron in our blood, was created later inside the cores of stars. This process is called nucleosynthesis, and it is slow, methodical, and requires time measured in cosmic epochs. A star must form, collapse under its own gravity, ignite fusion in its core, burn for millions or billions of years, and then, only in its death throes, forge the heavier elements through supernova explosions or stellar collisions. These elements are then scattered across space, seeding the next generation of stars and planets. This cycle must repeat, again and again, before galaxies become enriched with the metals necessary to form rocky planets, complex molecules, and eventually, life. This is the timeline we believed was written into the fabric of the cosmos. The universe aged like fine wine, slowly accumulating chemical complexity. The first generation of stars, known as population 3 stars, should have been massive, short-lived, and composed almost entirely of hydrogen and helium. Their deaths would seed the second generation, which would contain slightly more metals. Only after multiple generations spanning hundreds of millions or even billions of years should galaxies become rich in heavy elements. Yet when Webb spectroscopy pierced through the veil of the cosmic dawn, analyzing the light from galaxies formed just 300 to 500 million years after the Big Bang, it revealed something profoundly disturbing. These galaxies, infants by cosmic standards, were already enriched with oxygen, carbon, nitrogen, and silicon. Not in trace amounts, but in concentrations that suggested multiple generations of stars had already lived and died. The enrichment was not gradual. It was explosive, as if the universe had somehow accelerated its own chemical evolution, compressing billions of years of stellar cycles into a fraction of the time. This is the rapid enrichment problem, and it is one of the most unsettling puzzles to emerge from Webb's observations. The presence of heavy elements in such young galaxies implies that star formation in the early universe was not slow and measured, but frenzied and violent. Stars must have formed at rates far exceeding anything we see in the modern cosmos, burned through their fuel in mere millions of years, exploded as supernovae, and then immediately seeded new stars that repeated the cycle. The universe, in its infancy, was not a quiet nursery, but a forge burning at incomprehensible intensity. Webb's infrared instruments did not merely detect these elements, they measured them with precision. Spectrographs broke apart the light from distant galaxies, revealing the distinct chemical fingerprints embedded in their starlight. Oxygen lines appeared where they should not exist. Carbon absorption features suggested the presence of dust, another impossibility. Dust requires not just heavy elements, but time for those elements to cool, clump, and form solid particles. On Earth, dust is ancient. In the cosmic dawn, it appeared almost instantaneously. One of the most alarming discoveries was the oxygen abundance anomaly. Oxygen is a relatively heavy element, created primarily in massive stars through the fusion of lighter elements. It is expelled into space when these stars explode. Yet Webb found oxygen in galaxies so young that they should contain almost none. The concentrations were not merely present, they were abundant, suggesting that the first stars were not just massive but hyperactive, producing and dispersing oxygen at rates that seemed to violate the natural pace of stellar evolution. This raises a terrifying question. Where are the population 3 stars? These primordial giants, composed entirely of hydrogen and helium, should be the parents of all later stars. They should have left traces, remnants, evidence of their existence scattered throughout the universe. Yet we have never directly observed one. Webb, with its unprecedented sensitivity, has peered deeper into time than any instrument before it, and still, population 3 stars remain invisible. Either they are hiding in ways we do not understand, or they never existed in the form we imagined. Both possibilities are unsettling. Some scientists now propose that the first stars did not behave as predicted. Perhaps they were not solitary giants, but clustered in dense stellar nurseries where they influenced each other's evolution. Perhaps they burned hotter, died faster, and produced heavier elements more efficiently than our models suggest. Or perhaps the conditions of the early universe were so extreme that nucleosynthesis itself occurred differently, accelerated by forces or mechanisms we've not yet identified. Dust in the early universe presents another layer of impossibility. Dust grains are formed when heavy elements cool and condense into microscopic particles. This process takes time. On Earth, dust is the product of billions of years of stellar and planetary evolution, yet Webb detected dust in galaxies that had existed for only a few 100 million years. This dust was not sparse. It was thick enough to obscure starlight, creating dark lanes and nebulae similar to those we see in mature galaxies today. The universe, it seems, grew old before it had time to age. The implications for stellar evolution are profound and disturbing. Our understanding of how stars form, live and die is built on observations of the modern universe, supplemented by theoretical models that extrapolate backward in time. These models predict a slow, orderly progression from simple to complex, from hydrogen to heavier elements, from chaos to structure. Webb's discoveries suggest that this progression was anything but orderly. The early universe was a chemical inferno, a place where the rules of nucleosynthesis were bent, if not broken entirely. Every element detected in these ancient galaxies tells a story. Carbon, necessary for organic chemistry, appeared far earlier than expected. Silicon, the backbone of rocky planets, was already present in concentrations that imply the existence of solid worlds in the cosmic dawn. Nitrogen, essential for amino acids and life as we know it, was scattered across space long before life had any chance to emerge. The periodic table, it seems, was assembled not gradually, but with shocking speed, as if the universe was in a desperate hurry to become complex. Some researchers now suggest that the first stars were not just massive, but supermassive, with masses hundreds or even thousands of times that of our Sun. These stellar behemoths would have burned with unimaginable intensity, consuming their fuel in mere thousands of years before exploding in hypernovae so powerful they could enrich entire galaxies in a single event. Such explosions would have released not just energy, but vast quantities of heavy elements, seeding the cosmos with the raw materials for planets, moons, and eventually life. Yet even this explanation requires us to rethink fundamental physics. Stars of such immense mass should collapse directly into black holes, trapping their elements forever rather than dispersing them into space. Unless the conditions of the early universe, the density, the temperature, the magnetic fields, were so different that even the life cycle of stars operated under alternate rules, we are forced to confront the possibility that the early universe was not just younger, but fundamentally alien, a place where the laws of physics expressed themselves in ways we have not witnessed in the modern cosmos. As we analyze these chemical signatures, we begin to understand that we're not simply looking at data. We're reading a message written in atoms, a message that says the universe does not age as we thought it did. Time itself in the cosmic dawn may have moved differently, not in the sense of relativity or dilation, but in the sense of process, of transformation, of the speed at which complexity emerges from simplicity. The chemistry of the early universe is a chemistry of terror, because it reveals that the cosmos is stranger, more violent, and more accelerated than we ever imagined. The detection of these impossible elements forces us to ask deeper questions. If heavy elements appeared so quickly, what does this mean for the formation of planets? For the emergence of life? Could life have arisen far earlier in cosmic history than we thought possible? Are there worlds, ancient, beyond comprehension, where civilizations rose and fell long before our sun even began to form? The chemistry Webb has revealed does not just challenge our models, it opens doorways to possibilities we have barely begun to explore. And yet, the most terrifying aspect of this discovery is not what it reveals, but what it conceals. For every answer Webb provides, a dozen new questions emerge. If the first stars enriched the universe so rapidly, why did they disappear without a trace? If dust formed so quickly, what accelerated its creation? If oxygen, carbon, and silicon were abundant in the cosmic dawn, what other elements might be hiding in those ancient galaxies, elements we have not yet learned to detect or identify? The chemistry of terror is not about fear in the conventional sense. It is about confronting the limits of our understanding and realizing that the universe operates on principles we have not yet grasped. It is about staring at spectrographs and seeing not just lines on a chart, but evidence that reality itself is more fluid, more dynamic, and more mysterious than the equations we use to describe it. As we drift through the data Webb has returned, we are like travelers through Saturn's rings, surrounded by fragments of knowledge, each piece glittering with meaning, yet none fully understood. The heavy elements in the cosmic dawn are not errors or anomalies. They are clues, whispers from a universe that grew up faster than it should have, that became complex before its time, that broke its own rules in ways we're only beginning to comprehend. The chemistry of the early universe is a reminder that we are not merely observers of the cosmos, but students of a teacher that refuses to follow its own lesson plan. Every element detected is a word in a language we're still learning to speak. Every anomaly is a sentence in a story that does not follow the narrative we expected. The terror lies not in the darkness, but in the light, in what Webb has illuminated, in the impossible chemistry that shouldn't exist yet does, defying time, defying theory, defying everything we thought we knew about how the universe creates itself. When James Webb looked back into the cosmic dawn and found galaxies that should not exist, it did not simply reveal a surprising discovery. It opened a wound in the fabric of our understanding. For more than a century we have built a story of the universe, a narrative woven from mathematics, observations, and the careful testing of theories. We believed we knew how time began, how matter formed, how the first stars ignited in the darkness. But now, suspended between what we thought we knew and what Webb has shown us, we face a fundamental crisis. Not just in cosmology or astrophysics, but in our confidence that we can truly comprehend the universe at all. The discoveries Webb has made are not minor corrections, they are cracks in the foundation. When we find galaxies too massive, too bright, too structured, within the first few 100 million years after the Big Bang, we are forced to confront an uncomfortable truth. Something is profoundly wrong with our story. Either the universe evolved far more rapidly than our models predict, or the processes we thought governed cosmic evolution are incomplete, perhaps even incorrect. This is not a small problem to solve with a minor adjustment. It is a crisis that threatens to rewrite the entire narrative of existence itself. The question scientists now ask is not what did we miss, but rather, what did we fundamentally misunderstand? The lambda cold dark matter model, our standard cosmology, has guided us for decades. It describes a universe that expanded from a singularity, cooled through epochs, and gradually assembled structures under the influence of gravity and dark matter. But if galaxies formed faster, if black holes existed when they shouldn't, if chemistry appeared before it was possible, then perhaps the framework itself is flawed. Perhaps the universe does not follow the rules we believed it did. One potential solution lies in modifying our understanding of gravity itself. Since Einstein's general relativity, we have viewed gravity as the curvature of space-time caused by mass and energy. But what if, on cosmological scales, gravity behaves differently than we thought? Modified gravity theories suggest that at immense distances or in extreme conditions, gravitational forces may not follow the familiar equations. These alternative models could allow structures to form faster, matter to clump more efficiently, and galaxies to grow larger in less time. If gravity is not what we think it is, then the cosmic dawn becomes less terrifying and more explainable. But such a revision would shake the foundations of physics, forcing us to reconsider everything from planetary orbits to the expansion of the universe itself. Another path forward involves rethinking dark matter. For years we have assumed that dark matter is cold, meaning its particles move slowly and clump together gradually. But what if dark matter is more complex? What if it interacts with itself in ways we have not yet detected? Warm or self-interacting dark matter models propose that these invisible particles could have behaved differently in the early universe, accelerating structure formation and enabling galaxies to grow more rapidly. If dark matter is not a passive backdrop but an active participant in cosmic evolution, then the galaxies Webb has found may not be breaking the rules. They may simply be revealing rules we never knew existed. Yet perhaps the most profound possibility is that we need entirely new physics. The discoveries Webb has made may be the first hints of phenomena that lie beyond our current theories. Just as quantum mechanics and relativity revealed layers of reality invisible to classical physics, perhaps there are forces, particles, or principles operating in the cosmic dawn that we have never imagined. New. Physics does not arrive quietly. It arrives when observations refuse to fit into existing frameworks, when the universe insists on behaving in ways that defy explanation. Webb may be showing us the edge of our knowledge, the boundary where the familiar ends and the unknown begins. But these discoveries do not only challenge our models of the past, they alter our understanding of the future. The ultimate fate of the universe has long been tied to how it began. If the early universe evolved differently than we thought, then its trajectory forward may also be different. Will the universe expand forever, growing colder and darker until stars die and galaxies drift into isolation? Will it collapse back upon itself in a final cosmic contraction? Or is there another fate we've not yet conceived? The monsters in the cosmic dawn may hold the key to our cosmic destiny, written in the structure of galaxies that should not exist. Philosophically, these discoveries force us into a humbling realization. We live in a universe we do not fully understand. For all our instruments, equations, and centuries of observation, we are still children gazing at shadows on the wall of a cave. The confidence with which we once spoke of cosmic timelines and the formation of the first stars now seems premature. We thought we had glimpsed the beginning. Instead, we have found only questions, deeper and more unsettling than before. To be confronted with the limits of our knowledge is not a failure, it is an awakening. It reminds us that the universe is not obligated to make sense to us. It simply is, vast and indifferent, unfolding according to laws we're only beginning to perceive, and yet James Webb's work is far from complete. The observatory continues to peer into the cosmic dawn, probing deeper into the first billion years of existence. Future observations will examine the spectra of distant galaxies in greater detail, searching for clues in the light they emit. Webb will study the environments around supermassive black holes, trace the chemical signatures of the earlier stars, and measure the distribution of matter across the infant universe. Each new data set brings the possibility of confirmation or further disruption. Each observation is a test, not just of our instruments, but of our theories themselves. Upcoming discoveries may reveal even more anomalies. Perhaps Webb will find galaxies at even earlier times, pushing the boundaries of impossibility further back. Perhaps it will detect structures or patterns that current models cannot explain at all. The telescope's ability to observe in the infrared allows it to see through cosmic dust and capture light that has travelled across nearly the entire history of the universe. Every image is a window into deep time, every spectrum a fingerprint of ancient chemistry. As Webb continues its mission, the narrative of the cosmic dawn will continue to evolve, shift, and perhaps shatter entirely. This is both terrifying and thrilling for science. Terrifying because it exposes how fragile our understanding truly is. Theories that seemed solid now tremble under the weight of observation. Models that predicted order now confront chaos. The universe has reminded us that it does not care about our equations. It will behave as it chooses, and we must adjust accordingly. But it is also thrilling because this is how science advances. Not through confirmation, but through confrontation. Not by finding what we expect, but by discovering what we did not. The monsters in the cosmic dawn are not enemies of knowledge. They are its catalysts, forcing us to think deeper, question harder, and reach further than before. What Webb has found is not the end of cosmology. It is its rebirth. Just as the telescope revealed that Earth was not the centre of the universe, just as relativity revealed that time and space were not absolute, Webb is revealing that our story of creation is incomplete. We're being offered a rare gift, the chance to rewrite the story of existence itself. Not because we were wrong, but because the universe is more complex, more surprising, and more wondrous than we ever imagined. In the silence of space, billions of light years away, galaxies that should not exist continue to shine. They do not know they are impossible. They do not care that they challenge our models. They simply are, burning in the darkness, waiting for us to understand. And as we look back across the abyss of time, we realize that we are not merely observers of the universe. We are participants in a story still being written, one discovery at a time. The terror of the cosmic dawn is not that it shows us a hostile universe. It is that it shows us a universe beyond comprehension. And yet, we continue to look. We continue to question. We continue to search for meaning in the light of ancient stars. Because even if we do not understand, even if we are humbled by what we find, the act of looking is itself profound. It is the story of humanity, written in starlight, reaching back toward the moment when everything began. And so we return, not to Earth, but to the questions that haunt us in the stillness of the night. James Webb has looked into the cosmic dawn, and what it found does not comfort us. It terrifies us. It reshapes us. It forces us to confront the possibility that everything we thought we understood about the universe's birth may be incomplete, or worse, wrong. We've witnessed galaxies that formed impossibly fast, burning with light that should not yet exist. We have seen black holes at the edge of time, massive and ancient, defying the laws that govern cosmic evolution. We have discovered chemical elements forged in an era when the universe should have been too young, too simple, too raw to create such complexity. Each discovery is not an answer. It is a deeper question, a more profound mystery, a whisper from the abyss that time itself may not unfold the way we believed. The cosmic dawn was supposed to be a gentle awakening, a slow ignition of stars in the primordial darkness. Instead, Webb revealed a universe that erupted into violent, chaotic life almost immediately after the Big Bang. Galaxies appeared fully formed, spinning with ancient fury. Stars blazed in numbers that should have taken eons to accumulate. Black holes gorged themselves on matter, growing to monstrous sizes in what should have been the universe's infancy. This is not the story we were told. This is not the story we were prepared to hear. And yet, here we are, suspended in the silence of discovery, confronted by a cosmos that refuses to obey our models, our theories, our neat equations scrawled on blackboards in universities across the world. The universe, it seems, does not care what we think is possible. It simply is. And what it is, at the very edge of observable time, is terrifying in its implications. These discoveries matter not just for astronomers or physicists. They matter for every human being who has ever looked up at the night sky and wondered where we came from. If the universe began differently than we thought, then perhaps causality itself, the very foundation of cause and effect, operates under rules we have not yet comprehended. Perhaps time is not linear in the way we experience it. Perhaps reality, at its most fundamental level, is stranger and more alien than even our wildest cosmological nightmares have imagined. James Webb continues its mission, drifting in the cold expanse of space, its instruments trained eternally on the farthest reaches of observable existence. Every day it gathers more data, more images, more fragments of light that have travelled for over 13 billion years to reach its mirrors. With each observation, the mystery deepens. With each discovery, the questions multiply. We're not approaching answers. We're approaching a profound realization that the universe may be fundamentally unknowable, in ways we're only beginning to grasp. But this is not cause for despair. It is cause for wonder. The terror we feel when confronting these cosmic mysteries is not the terror of fear, but the terror of awe. It is the sublime experience of standing at the edge of human knowledge and peering into the infinite darkness beyond, knowing that what we see challenges everything, yet compels us to look deeper still. The abyss of time stares back at us through the lens of James Webb, and in that gaze we're reminded of our place in the cosmos, not as masters of understanding, but as witnesses to a universe far older, stranger, and more magnificent than we ever dared imagine. The cosmic dawn is not a beginning we can neatly catalogue. It is an ongoing mystery, an eternal question written in the language of light and shadow across the fabric of space-time itself. The journey continues, the observations persist, and somewhere in the data streaming back from Webb's golden mirrors, more revelations await, ready to shatter our understanding once again. If this journey into the cosmic dawn has moved you, if these mysteries have stirred something within, take a moment to like this video and let us know in the comments where in the world, or perhaps where in the universe, you're listening from tonight. Subscribe to join us as we continue exploring the deepest cosmic mysteries, the questions that keep us awake, and the discoveries that redefine what it means to exist in this vast, terrifying, beautiful universe. For now, rest well. The stars will still be there when you wake, ancient and patient, keeping their secrets in the endless dark.